In this video, we're going to investigate further properties of the gradient vector. In addition to the fact that the gradient vector points in the steepest uphill direction. That's going to be our touchstone for everything, but these other derived properties are often useful as well. All right. The gradient of f is perpendicular to the contour of f that passes through the point. Well, does that make any sense? Well, let's imagine a contour with a certain label on it. So say height 2, and then another contour over here at height 3. And we pick a point here, AB. What we're saying is that at this point, the gradient will be perpendicular to the contour. Well, we can see that makes some sense graphically. If we are trying to get from height 2 to in the steepest direction to get to contour at height 3, we should go in this direction of the green arrow. And we notice that that is perpendicular to the contour we're on currently. You can think of it as getting away from this height as fast as possible. How do we get away from a line? We move perpendicular to it. But even better, we can validate that through a calculation. If we think of our directional derivative again, which is equal to the gradient vector dotted with the direction of travel, if we stay on the contour, then what we get is a slope of 0. If we follow this contour, small microscopic step, then we do not change our height, and so our slope would be 0. And so what we can do is identify that the slope would be 0, so 0 would equal the gradient of f dotted with u. And so the gradient of f is perpendicular to a vector if this vector here follows the contour, or is tangent to, is more explicitly correct here. So if we had one of our options being going in this direction, that being u, we take a microscopic step, we do not change height because we stay on the contour. The gradient is going to be perpendicular to that to allow that slope to be 0 in the directional derivative calculation. Another property that is handy and has the same kind of flavor as these is knowing that going perpendicular to the gradient goes 0 slope, going in the direction of the gradient is uphill in the steepest direction. Well, if we turn 180 degrees and go down, we're going to find that negative gradient of f is the steepest downhill direction. We can envision this by imagining ourselves standing on a hillside, and if we turn in one direction, see that's the direction that'll take us uphill in the steepest direction, and then we turn perfectly around 180 degrees and look down, we'll see that we'll be going downhill in a very steep direction, at least for small steps. Now, of course, we can validate this with the contour diagram or through the calculations again of the directional derivative. If we want to compute the gradient dotted with u, which is the slope in the direction of u, and if our goal is the largest negative d value, then what we're going to want is the gradient of f dotted with u, but that can be computed by the alternative dot product, the angle-based dot product. Again, the gradient is a vector that we get at a certain point, it's fixed. The vector u is always a unit vector, so it's always length 1. And that leaves us choosing the cos of the angle between them. Well, the direction that's going to give us the maximum negative value here, want the largest negative value. Well, the largest negative value cos ever takes is -1, and that comes with theta being pi radians, or 180 degrees, and that tells us that to go in the steepest direction downhill, we're going to take the gradient vector, but then invert it or go 180 degrees relative to it. That'll produce the steepest downhill slope. Last but not least, the magnitude of the gradient vector itself actually has some meaning. Again, if we think of the slope in the direction u, f of ab, is equal to the gradient dotted with the direction we pick. And now we pick u to be in the same direction as the gradient of f, or the little triangle symbol, gradient of f there. Then we get the angle between them is 1. Sorry, the angle between them is 0, which gives us the cos of the angle between them is 1. And we pick u in that direction, but we keep u being a unit vector. So if the gradient is big or small, doesn't matter. We just pick u in the same direction, but length 1. If that's the case, then we can fill in our dot product calculations again here. And because of the way we picked u, this is going to equal 1. Because u is a unit vector, this is going to equal 1. And this is the only thing left over. So the slope in the direction of u, but we picked u to be the direction of the gradient vector, is equal to the magnitude of the gradient vector. So not only do we learn information about the steepest direction, in other words, out of all the directions we could move, the gradient points uphill in the steepest direction, the value of the elements or the components of the gradient tell us something about how steep it actually is in that direction. Is it shallow slope or steep slope on the surface at that point? So a lot of derived information just by knowing this package of the x derivative and the y derivative as a vector. That package gives us a whole pile of information about the surface at any given point. Let's see if we can connect that to this contour diagram here, a little more involved than the linear ones we've worked with already. For each of the points a, b, and c, draw a vector that points in the direction of the gradient vector at that point. And the key things that we use for this are the gradient vectors point uphill, and they point perpendicular to the contours. With those two pieces of information, there's only one vector you can draw in every case. From A, we notice the heights are getting higher this way, heights are getting higher here, so these are peaks. If we're going to go uphill, it'll be in that direction there, and it has to be perpendicular to the contour. It won't be back in this direction because that would be downhill, and the gradient by itself points in the uphill direction. Likewise at B, we would have a vector that points uphill and perpendicular to the contour. C, the same thing. If we draw our contour here or see our contour here, we go perpendicular and up the hill. So that's the direction. Now, the length of the gradient vector is what we're going to look at next. Well, the gradient vector length corresponds to the steepness in the gradient vector direction. So what this is asking for is how steep is it if we take a step in the direction of the gradient. And out of these 3 points, if we look at the density of the contours are most dense around C, so this gradient vector would be longer. And there's actually no geometric relationship. It could be that the gradient vector is actually huge in terms of the units that we're using, but all we know for sure, without any extra information, is that the C vector would be longest. And looking at the density of the contours locally, so right around the point, it looks like A would have the next largest and B would have the smallest. Because it takes the longest time to get to the next contour for B, that indicates a more shallow slope certainly compared to C, and marginally compared to A. We get to the next contour a little bit sooner, going in this direction, if we are at the point A. So that's reflecting all of the properties we just talked about for the gradient itself in terms of its direction and also its magnitude.